Hey everyone, and welcome to The Explainer. I am literally so excited to be your technical mentor today. Because if you've been banging your head against the wall trying to get your hardware to run smoothly, you are absolutely in the right place. Today, we're going to demystify one of the most fundamentally important, but honestly widely misunderstood, concepts in all of hardware engineering and hobbyist electronics. I'm talking about the PID loop. By the end of this explainer, you're going to know exactly how to diagnose, tune, and completely master your hardware's stability.
So, we've all been there, right? You build or upgrade a piece of hardware, you power it on, and instead of flawless performance, you get, well, incredibly frustrating behavior. For my 3D printing makers out there, maybe your hot end temperature graph looks exactly like a sine wave. It's constantly swinging plus or minus 3 degrees around your target. And you know that 6-degree swing isn't just an ugly graph, it means inconsistent extrusion, terrible visible banding on your prints, maybe even nozzle clogs. Or for FPV drone pilots, maybe you pull off a sharp flip, and instead of a crisp, clean snap to your new angle, the quad stutters and wobbles. Both of these totally different hardware headaches actually stem from the exact same root cause, a poorly tuned control loop.
To fix these issues, we really need to understand what's actually going on inside the black box of your firmware. PID stands for proportional, integral, and derivative. At its core, a PID controller is just a really versatile closed-loop control mechanism. It constantly measures the difference between where your hardware currently is and where you want it to be, a target we call the set point. It calculates the optimal output by looking at three very distinct things: the present error, the accumulated memory of past errors, and a prediction of future error. These three branches work dynamically together to drive your hardware's error down to absolute zero.
Okay, let's dive right into this. Here is our roadmap for today. First, identifying overshoot. Second, how PID controllers work. Third, comparing 3D printers versus drones. Fourth, fixing common mistakes. And finally, essential hardware safety. All right, starting with section 1, identifying overshoot.
And this brilliantly illustrates what we're looking for: a universal symptom of a poorly tuned system. When a command is given to change the state of the hardware, that's our blue line, the hardware reacts. See that red line? It just rockets past the target command, drops way below it, goes back above it, and kind of slowly ripples out. We call this an underdamped response, and it's exactly what we want to avoid. Our goal as tuners is the green line, a critically damped response. That's where the hardware achieves the fastest response to a command change possible without ever overshooting or oscillating.
In the field, we usually just call this physical overshoot bounce back, and it is incredibly common. If you're flying a quad, bounce back is that terrifying little physical shudder or shake you see in your FPV feed right at the end of a sharp roll. The quad overshot the rotation rate you commanded, and it had to actively bounce back to it. If you're working on a 3D printer, bounce back is your heated bed rocketing past your 60-degree target, hitting 65, and taking a full 30 seconds to settle back down, which, by the way, absolutely warps your first layer. Bottom line, bounce back is the ultimate indicator that your PID tune is fundamentally off.
Moving right along to section 2, how PID controllers work. Let's actually break down the theory here so we know how these three magical letters interact. The process starts when the system calculates the error, which is just the difference between your target and reality. That error splits into three paths. The top P path, proportional, provides the immediate physical muscle and reaction to your current error. The middle I path, integral, integrates past errors to fix steady-state offsets. Like if your drone is stuck hovering just slightly below altitude, the I term builds up over time to nudge it exactly onto the target. Finally, the bottom D path, derivative, reacts to the rate of change. It acts as a dampener, essentially predicting the future to apply the brakes so the P term doesn't overshoot. Now, what's really cool is how directly these theories translate to practical workbench symptoms. Take 3D printer hot ends, for example. If your proportional gain is too low, your heating is going to be super sluggish and it'll droop wildly when the cooling fan kicks on. If your integral term is too low, the temperature just stabilizes a few degrees below your target. And the derivative term? That one's fascinating. If D is too low, you get that overshoot and ringing. But if D is too high, it leads to a noisy output where the heater flickers rapidly and erratically. Finding the perfect balance between these three forces, that's the whole game. Which brings us to section 3, 3D printers versus drones. You see, while the math of a PID controller is universal, the physical environment completely dictates how we tune it. You can never ever just copy and paste tuning logic across different types of hardware. A 3D printer operates in a world of really slow thermal mass. We're dealing with heat blocks, silicone insulating socks, cooling fans. The control loop is slow, taking seconds or even minutes to cycle. A
A drone flight controller, on the other hand, operates in milliseconds. It needs extreme aerodynamic agility and constantly fights an influx of high-frequency noise, specifically motor vibrations ringing right in that 100 to 200 hertz range. Because a drone's D term is highly reactive to fast changes, this vibration noise can actually cause your motors to overheat if you don't manage it properly. Let's get into Section 4, Fixing Common Tuning Mistakes. Time to get our hands dirty. For you FPV pilots out there, your tuning procedure has to follow a strict order of operations. Step 1 is actually not PID tuning at all. Well, scratch that, it's filter tuning. Because the D term doubles its gain response as noise doubles in frequency, high-frequency noise will drive your D term absolutely crazy. You have to use your gyro and low-pass filters to crush motor vibration noise first. The PID controller literally cannot work well if it's actively fighting raw vibration. Only after your filters are totally clean do you move to Step 2, tuning the P and D balance, and finally Step 3, increasing your overall PD gain for tighter stick tracking. And that brings us to configuring that balance. If you use Betaflight, you'll see a specific slider for PD balance. This is simply your P gain divided by your D gain. Your goal in Step 2 is to do sharp rolls and flips, and just keep raising your P gains relative to your D gains until you visually see, or even audibly hear, a sharp bounce back. Once you hit that overshoot, you just back it down slightly. You are hunting for the highest P over D balance possible without inducing that underdamped oscillation we talked about earlier. Once you find that perfect ratio for your specific rig, lock it in. Now, for my 3D printing makers, you've got a way more automated workflow. Whether you're running Marlin or Clipper, you just run an auto-tune command. But here is the secret. You absolutely must set your part cooling fan to the speed you actually print at before you run the command. Then let the auto-tune run for 8 to 10 heating cycles. The printer will heat up, cool down, and pulse the heater to measure the precise thermal response of your specific block. Save the parameters, test it, and a perfect tune is going to give you a beautifully flat temperature line hovering within just plus or minus 0.5 degrees of your target. But listen, even though auto-tuning is super easy, so many people fall into the exact same traps. If you tune with your fan off, your firmware learns a gentle thermal response. So mid-print, when your fan kicks up to 100%, your nozzle drops 5 to 10 degrees because the PID loop just isn't aggressive enough to compensate. Also, please, never skip bed PID tuning. Default profiles assume a bare PCB heater. If you add a glass plate or PEI sheet, you've completely changed the thermal mass. Don't copy profiles from Reddit either. Your Ender 3 with an all-metal hot end reacts totally differently than a stock one. Anytime you change a nozzle or add a sock, you gotta retune. All right, final section, essential hardware safety checks. Okay, real talk for a second. Stability is awesome, but safety is non-negotiable. The crucial point here is that a perfectly tuned machine is totally worthless if it burns your workshop down. 3D printers operate at incredibly high temperatures with high amperage components. You must always verify that thermal runaway protection is enabled in your firmware. Never, ever bypass that. Check your physical wiring too. Make sure your heater cartridge wires are secure and not frayed. Put a dedicated smoke detector right above your printer. And definitely look into the 2026 fire safety standards, which highly recommend adding physical thermal fuses to heated beds as a final physical fail-safe. Well, you did it. You've successfully diagnosed overshoot, dialed in your proportional, integral, and derivative paths, and secured your hardware safely. You've officially eradicated the sine waves and the wobbles. But don't pack up your workbench just yet. Now that your thermal and rotational stability is completely locked in, you kind of have to wonder, what's next? Are your extruder's E-steps perfectly calibrated? Is your drone's feed-forward transition fully optimized? Hardware mastery is this endless, fascinating journey. Take these new PID skills, enjoy that incredible performance boost, and start looking for the next bottleneck to conquer.